Question 6. So take a good look at the diagram, make sure you've picked up all of those forces, make sure you've broken the weight force down into the two components here in red, and remember the friction equals the coefficient of friction times the normal reaction. That's the normal reaction going off perpendicular. So on this occasion, with the coefficient being a half, F equals a half R. The other thing, again, it cropped up earlier in the paper, because tan alpha equals 3 over 4, cos alpha is 0.8 and sin alpha is 0.6. Now for part A, we just resolve in this direction, so R equals 0.3g cos alpha. Cos alpha being 0.8, so R equals 2.352. Now for part 2, in order to work out the mass, we're going to create a simultaneous equation. First of all, looking at P and resolving up the slope. The forces obviously don't balance because we've got acceleration, so we're going to Newton's second, that F equals ma. So our net force is on the left hand side, T minus F minus this red bit, which is 0.3g sin alpha, and that equals the mass times the acceleration, so 0.3 times 1.4. Simplifying this, we get this equation with, well, it would allow us to work out t, but we're just stopping at that point there. Now then moving on to looking at q. So we're resolving up and downwards, so we've got again we've got the acceleration, so Newton's second again, F equals ma. Our net force downwards is mg minus t, equaling m times a. This allows us to get 8.4 m equals 3.36 once we've gone and added 1 and 2 together. So I've just taken that equation there, I've taken that equation there, adding them together eliminates t. This allows me to work out m being 0.4. Equally, I could have just I could have made t the subject here, worked out t, and then just substituted that into this equation here. But either way, we can, from our two initial equations here, however you've done it, you can work out the mass to be 0.4 kilograms. Now for part C, we're going to be looking at what happens after 0.5 seconds. So we're going to be using V equals U plus AT, but we need to work out the initial speed after the string breaks and also the acceleration the particle will be travelling at. So first things first, the initial speed when this string breaks is the final speed just before the string breaks. So looking at that first, well, initial speed is 0, an acceleration of 1.4, a time of 0.5, using V equals U plus AT. We see the final speed of this first phase up to 0.5 seconds is 0.7 meters per second. So that's our initial speed after the spring breaks. Now secondly, let's consider the acceleration once the spring is broken. So we need to resolve again up the slope, the difference being that there is now no tension, the tension is gone. So we're just basically reusing this formula here, but without t. Remember, the magnitude of the normal reaction and hence the friction will not change. That does not change. So we're simply just solving with t now absent. This gives us a being minus 0.98. So substituting that in, so now that we know A, we know U, we can again use V equals U plus AT, because we know our final speed is going to be 0, because we're trying to work out the time until it comes to rest. So V is 0, so substituting into V equals U plus AT, we get T being a 14th, which is 0.071 seconds.